Hello, my name is Magnus Petersen. This is my tutorial number 19 on TensorFlow, and this is about hyperparameter optimization. And if we go back and look at the flowchart for tutorial number 3, for example, here we have the basic structure of a neural network. We have an input image, convolutional layer, another convolutional layer, a fully connected layer, and an output layer. There are a lot of parameters here. For example, the number of filters in the first and second convolutional layers, and the size of those filters. And also the number of convolutional layers, and the number of fully connected layers, and the number of features or nodes or elements in each of those layers. Furthermore, there are parameters used by the optimization method, for example, the learning rate, and all of these parameters can be modified by the user, and some of them have a great effect on how the neural network performs. So how do we find them? Well, there are different ways of doing it. And one way of doing it is by hand tuning. So if you remember the previous tutorials, a lot of the exercises have been try a different set of parameters for the number of fully connected layers or how many nodes in each of those layers and the learning rate and so on. If you do this a lot, you can get some kind of intuition about what parameters work well. The problem is that it is not only extremely time consuming, but the optimal choice of hyperparameters is often counterintuitive, and this means you probably won't even find the best parameters. Another way of doing it is to take the valid range for each of the parameters and divide it into evenly spaced intervals, for example 10 intervals, and then you try all combinations of parameters on these intervals, and this is called grid search. The problem with this is that not only do you get a fairly coarse division of each parameter, for example only 10, but the number of possible combinations grows exponentially as you add more parameters. For example, if you have just 4 hyperparameters and each of them is allowed 10 possible values, then there is a total of 10 to the power of 4 combinations of these parameters. If you add just one more hyperparameter and also allow it 10 different values, then the total number of combinations for all parameters is now 10 to the power of 5. And this is also known as the curse of dimensionality. Another way of doing it is by completely random search, and this is like searching for a needle in a haystack. And the problem here is that as the number of parameters increase, the probability of finding the optimal parameter combinations rapidly decreases to 0, so it is extremely unlikely that you're ever gonna find it by random search. Now what we're gonna use in this tutorial is an awesome library called scikit-optimize, and I gotta tell you, I am really excited about this. I have mixed feelings about it, and I will get back to that later, but it is awesome. And I think that the reason I really like this is I worked in a related area, maybe 10 years ago, called meta-optimization. We wanted to optimize some actual problems, and we had an optimizer for doing that, for example, particle swarm optimization or differential evolution. And what I did was I took another very simple heuristic optimizer and put on top of that and called it the meta-optimizer. And the strength of my method of doing this was that it was very simple and it was reasonably effective. A few years ago, I wanted to improve my Python skills, so I converted my old code to Python, and you can find it on my GitHub page here. And it can do this meta-optimization, and the best method for it was this one here called local unimodal sampling, and it's a stupid acronym I invented because lus means louse in Danish, and I thought that was funny. You know, that's how it goes. But the reason I'm really excited about scikit-optimize is that it is a far more sophisticated way of doing it. It is far superior to my simple way of doing it 10 years ago. And this can be used on neural networks like I will show you in this tutorial here. It can be used on heuristic optimizers, as I did with my old work. And it can be used for a million other things where you have some problem that is extremely expensive to evaluate and you want to tune some parameters. So you can only perform maybe 40, maybe 100, maybe 200 evaluations of different parameter choices. You can't do 10,000 or 100,000 or anything like that. So let's take a look at how you would do this using scikit-optimize. They have different methods of doing it, but they're all based on so-called Bayesian optimization. And what we will be using in this tutorial is called a Gaussian process. The idea is that you have this true objective function or fitness function, and you want to find the minimum or the maximum. Now in our case, we don't know what the true fitness function is because it is the performance of a neural network on some data set. And In order to find out how the neural network performs with a given set of hyperparameters, we need to train that network, and that takes a long time. Now we are going to do it on the MNIST dataset, which is fairly quick. But on a real-world problem, this might take you hours or days or weeks on a very powerful computer. So you simply don't have the computational time to evaluate that many different choices of hyperparameters. So what we show here in this little plot is the true objective function with a range of noise. And the red dots here show where scikit-optimize has sampled the search space for hyperparameters. And this only shows one dimension, but you should imagine that this goes up to any number of dimensions. And what it does is that it builds a model called the Gaussian process. And these are the green lines here shows the mean. And in areas where we have a lot of hyperparameters that we have already tried, the Gaussian process will have a quite accurate estimate of what the true fitness value really is. But in areas like this here, where it doesn't really have any samples, it has a great uncertainty about what the true fitness value is. So you see that as the green line here, the dashed line, is quite different from the true fitness value in the red line here. And it also gives you an estimate of how big this uncertainty is. So the green area here shows you that the Gaussian process thinks that the true fitness value may actually be somewhere in here. And I think this shows something like 2 standard deviations or the 95th percentile or something like that. So the idea is that we ask for a new set of hyperparameters. We might say early in the optimization, we like to explore more of the search space. And then later in the optimization, we might try to exploit one of the best regions that we have already found. So at first it spreads out the samples, and later it will start to focus on a region that it knows is quite good. And to see more details on the many different schemes on how you can do this, you should watch a lecture on YouTube. There are several of them that explains expected improvement and probability of improvement and the various different schemes. But anyway, what we get out of this Bayesian optimization is a set of hyperparameters. And in our tutorial here, we will use the learning rate, the number of dense or fully connected layers in our neural network, the number of nodes in each of those layers, and the activation function, whether it should be sigmoid or ReLU. We send these hyperparameters to a function that creates a neural network using these parameters. Then we train that network on our dataset. We will use MNIST here, but you can use any dataset you want. Then we evaluate the performance of the neural network. We get the classification accuracy on the validation set. And then we update this model up here, the Gaussian process or the Gaussian model. And then we repeat this a number of times until the Gaussian process is fairly accurate and it has found a good set of hyperparameters. And what you see up here is what the library scikit-optimize will do for us. So as usual, we need a bunch of imports. We need NumPy and a bunch of things from TensorFlow and Keras. And because we will save and load the model using Keras, you also need to have something called h5py installed. And you also need to install scikit-optimize, and you should be able to do that using this command here. Now, I actually had to make quite a few modifications to various parts of scikit-optimize, and that has not yet been merged into the official release of scikit-optimize. So I hope that gets done in maybe a week. But this is one of the problems with scikit-optimize, is that it's a fairly small number of people who are working on it, and they do it in their spare time. So if you have a problem, it can take a very long time for it to get fixed, if it gets fixed at all. And even if you fix it yourself, for this to get reviewed and merged into the official release can also take a very long time. So if you want to run this before it has actually been merged into the official release, you will have to run this command down here to install it from my development fork on GitHub. And then you can run this notebook. And once you have that installed, you need to import a bunch of things from scikit-optimize as well. And as you see here, I used scikit-optimize version 0.4, but it's a development fork. And hopefully by version 0.5, it should be able to run this notebook fine. So once again, what we want to find in this tutorial are 4 hyperparameters for a neural network. We want to find the best learning rate for the optimizer of that neural network, and we will use the ADOM optimizer that we have used in several tutorials. We want to find the number of fully connected or dense layers that is optimal for classifying the MNIST dataset. Then we want to find the number of nodes for each of these dense layers. And then we want to find out whether we should use sigmoid or ReLU activation in all the layers in the neural network, including the convolutional layers. So to set up this hyperparameter optimization with scikit-optimize, we first need to define what is called the search space dimensions. So for each of these hyperparameters that we want to find, we need to define one of these dimensions. So first we have the dimension for the learning rate. And this is a real number or a floating point number. And we say that it must be between the lower bound of 10 to the power of minus 6 and the upper bound must be 10 to the power of minus 2. This is an exponential search range, and it is a lot better to search between minus 6 and minus 2. So we use a logarithmic transformation first, and this is handled automatically by scikit-optimize. We also need to give it a name, and this name will be used when we call the function for training and evaluating our neural network further below. Then we have another dimension for the number of dense or fully connected layers in the neural network, and this can take on integer values between 1 and 5, and we call it num-dense layers. Then we have the number of nodes in each of these dense layers, and we say that this can be an integer value between 5 and 512, and we call it num-dense nodes. Finally, we have what is called a categorical dimension for the activation function, which can take on the value ReLU or sigmoid, and these are strings. And this is also pretty awesome that scikit-optimize can automatically combine dimensions of different types. And depending on what kind of Bayesian optimization you are using, these dimensions might be mapped to something else internally. For example, for the Gaussian process, it will actually map this categorical dimension to a one-hot encoded array. But I won't go into details how that works because it's all pretty much transparent for the user. And when we have defined all these dimensions, we just create a list with all of them. Now, it is helpful to start off the hyperparameter optimization using a choice of parameters that we know works well. The MNIST dataset is fairly simple, so it is easy to find parameters that work quite well. So I have chosen parameters here that are not that good. They are not horrible, but they are not that good either. And because scikit-optimize uses lists internally that do not have names for each of the variables, we need to define these variables in a list in the same order that we have done up here with the dimensions. Okay, so we need a bunch of helper functions for doing various things, and this one is because we want to use TensorBoard to display the loss values for training each of the neural networks with a different choice of hyperparameters, and I'll show you that further down. In order to do that, we need to create a lock in TensorBoard, and I haven't made a tutorial on TensorBoard, but there are several on YouTube about that. But it's basically a tool for visualizing what is going on during the training of a neural network in TensorFlow. And this helper function just creates a directory name based on the hyperparameters. And this lets us separate the log files that are recorded during training of each of those neural networks so they can be shown individually in TensorBoard. And we also need to load the MNIST dataset, and we have shown this in many other tutorials. And we define all the dimensions for this data. And yeah, this is kind of a stupid name. This is because I have, of course, just cut and pasted this from previous tutorials. So this should not be confused with dimensions for the hyperparameter search space. I apologize for that confusion. Then we have a helper function for plotting images, and this is also just taken from previous tutorials. And we can plot a few images from the test set to see that they have been loaded correctly. And finally, we have a small helper function for plotting some example errors, which we will use further below as well. Okay, so now we get to the point where we're going to set up the hyperparameter optimization. First, we need this function for creating the neural network. And this takes the hyperparameters as arguments, and then it uses Keras to build what is called a sequential model. And you should watch tutorial number 3C for more details on this. And then we add input layer, we reshape it, we add the first convolutional layer. And you can see there are many parameters here that could also be optimized in the hyperparameter optimization. And this is an exercise that you should try and do. But in this tutorial, all we want to do is find the best choice of activation function. So we use activation here, which we got in up here when we called the function. And we do the same for the second convolutional layer, and then we flatten it so we can input it to dense or fully connected layers. And remember that we have a hyperparameter that we want to find for the number of dense layers. So we have this for loop that creates this number of dense layers. And here we also use the hyperparameter for the number of nodes and for the activation function. Then we add a dense or fully connected layer with the softmax activation. And then we use the ADAM optimizer with the hyperparameter for the learning rate. And in Keras, we need to compile the model. So we do that and we return it. So this function has built a neural network using the hyperparameters. And then it returns that model, but it has not trained it yet. So before we make the function for training the model, we first define the path for where we will save the neural network that performs the best, so that we can easily reload it later. And we just have a little global variable here for keeping track of the classification accuracy for the model that we have saved in this path. And then we create what is called the fitness function, or the objective function. And this is the function that scikit-optimize will call. Internally, scikit-optimize uses arrays, like this one for example here, where it has the learning rate, the number of dense layers, the number of dense nodes, and the activation function. And scikit-optimize uses this style because it wanted to be compatible with another library called scipy. Personally, I don't like the scipy API very much, but it's not my decision to make and it's already done. I prefer to call the function with the names of the dimensions used as function arguments, because what this means is that, first of all, you don't have to unpack the parameters from a list to individual parameters. And secondly, that means there's much less risk of making bugs if you forget one of the parameters or if you change the order of how you define them in the search space dimensions. So what I did was I added this function decorator to the scikit-optimize library. And I cannot take full credit for this. I had originally done it in a different way that I thought was better because it was more transparent to the end user. But the developers didn't like that so much because it added another argument to the optimization methods that we're going to call further below. And in collaboration, we came up with this as a good solution. So what it does is that it takes this function, which uses named arguments, and then it converts it into another function that takes a single list as an argument, like here, and then automatically it converts between this list here and the named argument. So it's completely transparent for the user if you just add this decorator to your fitness function. Inside this function, we just print the hyperparameter so that we can see them while it's running. And then we create the neural network using the helper function that we had made above. And you could have all of that code inside this function, but I like to keep it separate so we don't have one gigantic function that does a whole bunch of things. And then we have to get the directory name for the log files for TensorBoard using the other helper function that we had made above. And then we have to create a callback function for Keras. And this will be run after each of the training epochs has ended. And this saves the log files for TensorBoard. And this has not completely been implemented. There are some issues with it if you set this histogram frequency to 1, so it doesn't log all of the data that we'd like to see, but maybe I'll do that in the future. And then we use Keras to train the model, and for this simple data set, we will just run 3 training epochs, and we will use a batch size of 128. These are actually also hyperparameters that you could optimize using scikit-optimize. And when that training is done, we get the classification accuracy on the validation set, and that has already been calculated by Keras, because in the fitting function here, we give it the validation data. And then we print that classification accuracy, and then we compare it to the best classification accuracy for the hyperparameters that we have previously tried. And if it is an improvement, then we save this neural network to disk so we can reload it later. And here is something that is actually quite important, because we have to delete the Keras model that we have just built, and we have to clear the Keras session. If we don't do that, it will keep adding new neural networks to a TensorFlow session until finally it runs out of memory. So what we do here is that we just say to Keras, remove everything that we have just built so we can start building a new model. And then we return the negative classification accuracy on the validation set. And the reason that we negate this is that scikit-optimize performs minimization. So it tries to find the set of hyperparameters with the lowest fitness value or the lowest objective value. And because we're interested in the highest classification accuracy, what we do is simply take the negative classification accuracy so that now it's a minimization problem instead of a maximization problem. Now, before we actually run the hyperparameter optimization, we just try and call our fitness function with the default parameters that we have chosen above. So remember that these were the parameters here, where we have the learning rate, the number of dense layers, and the nodes in that layer, and the ReLU activation function. So when we call the fitness function that we have just defined using these default parameters, it will first use Keras to build the neural network using these hyperparameters. Then it will train it 1, 2, 3 epochs. And this has the classification accuracy of 66.54% on the validation set. So now let's do the actual hyperparameter optimization. And I think this took maybe 10 minutes to run on my laptop PC with a GTX 1070 GPU. And the way we run this is that we call this GP minimize function from the scikit-optimize library. And they have other functions, and it's an exercise that you can try one of these other optimizers and see how they perform instead. So we need to give it the objective or the fitness function, and this is just the function that we defined above. And then we give it the search space dimensions, and we give it what is called the acquisition function. And here we use expected improvement. And if we just go back to the flowchart, I'll show you here that the acquisition function determines how the Gaussian process is being sampled. So I think expected improvement takes a sample in the search space that maximizes the expected improvement to the best known position, I think. But again, you should watch one of the lectures on Bayesian optimization to get the details on the different acquisition functions. And then let's go back down. So this here means that we want to call the fitness function a total of 40 times. And this here means that we want to first try our default set of parameters. So you can see when this has been run, it first tries the parameters that you just saw above as well. And it gives a classification accuracy of 61.66% because there is this random noise depending on the training of the neural network and how all the weights and bias values in the neural network were randomly initialized. It might end up with slightly different results. But anyway, this runs for about 10 minutes on my GTX 1070 GPU on a laptop PC, and it just continues. So here we get another set of hyperparameters. This builds another neural network, runs the training, gets a classification accuracy on the validation set, and this is used to update the Gaussian process. And then it uses the acquisition function to get a new set of hyperparameters, these ones here. Then it trains another neural network, and this continues 40 times. Until finally, at the end, we have these hyperparameters here, this learning rate here, 2 fully connected or dense layers, each of them having 326 nodes, and using the sigmoid activation function. Now, this is not necessarily the best set of hyperparameters. These were just the ones it tried last. And scikit-optimize has a number of plotting functions built in, and this one shows the progress of the optimization. So it takes the number of calls to our fitness function and the fitness or the objective value that it has returned. So this is for the default set of parameters that we started with, and already in the second try, it found much better parameters, but this was pure luck, and that is because the MNIST dataset is fairly simple. But what you will probably see on a more challenging dataset is that this goes down gradually, while the Bayesian optimization finds better and better parameters. So the best hyperparameters that we have found were these. And again, scikit-optimize uses lists of parameters internally, and we can use a helper function to convert this to a dict. So we can see that the activation function was ReLU, and the learning rate was this one here, and the number of dense layers were 4, and the number of dense nodes were 144. And the fitness value for these parameters is minus 0.98799999. And again, remember that this is actually the negated classification accuracy on the validation set. We can also print all of the hyperparameters that scikit-optimize has tried, and we can sort them by the fitness value or the negative classification accuracy, and we get them out here. And we can see that it appears that all of the best ones used the ReLU activation function, but the other parameters are really quite difficult to see any pattern of what might be a good choice of parameters. So we really need to plot this. And fortunately, scikit-optimize has a number of plotting functions already built in. Actually, this is one that I have added. The problem was that the plotting functions didn't support categorical dimensions, so I had to rewrite all of them so that they could either ignore the categorical dimensions, or in this case, we could plot it separately. So what this shows is that we have 40 samples of hyperparameters in total, and 25 of these had used the ReLU activation function, and 15 had used the sigmoid activation function. And already here we get an indication that maybe ReLU was better because it has sampled those more. And we can also plot a landscape of the fitness value when we change two of the hyperparameters. For example, the learning rate and the number of dense layers as shown in this plot here. And this is what is called a partial dependence plot. We actually have 4 dimensions. So it takes a whole lot of random samples for all 4 dimensions, and then it fixes the learning rate and the number of dense layers at evenly spaced points. For example, here, 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 and so on. And here, 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 here. So it has a fairly fine grid of values. And then for each of these points, it will calculate the fitness value for all other parameter combinations that we have sampled. And then it will take the average fitness value and use it here. And it continues doing that for all of these points in the grid. And then it draws this contour plot that you see here, where the yellow colors means that the fitness value is lower and hence better. And the blue or purple colors means that the fitness value is higher and hence worse. So what it has found is that a learning rate around here is much better than a learning rate out here or a learning rate here. This is really the optimal region when averaged over all the other hyperparameters that we are trying to find. We can also plot this for other dimensions, but it cannot plot it for categorical dimensions. So we just make a list of the dimension names that we want to use here. And this is something that I have added to scikit-optimize, and this is one of the things that is not yet in the official release. And I had to rewrite the entire file for plotting functions in scikit-optimize because I found their code so difficult to understand that it was really difficult if I had to add these features to their code. So I just rewrote everything. And instead of going into a long rant in this tutorial about everything that was wrong with their code, I actually made a separate video that goes into details about how I converted their code. So when we plot this, we get this sort of matrix with plots. On the diagonal, we have what is called the partial dependence plot for a single dimension in the search space. So for example, this one, we have the learning rate. And what it does is it takes a large number of samples randomly in the search space. Then it fixes the learning rate, for example, here. And then it calculates the fitness value that has been estimated by the Gaussian process for all of the other random samples in the search space. But with this fixed learning rate here, then we take the average of all those fitness values and we plot the value up here, and we repeat this at intervals for different learning rates until we get this curve here. So what this shows is how the fitness value changes on average when we change the learning rate. So if you are only allowed to change the learning rate and you take some random choice for all the other hyperparameters, then it would appear that the best choice of learning rate is here. And if we just scroll down a little, we'll see that it is something like 10 to the power of minus 3 or something like that. And we can also plot this for the number of dense nodes. And here the partial dependence plot indicates that higher number of dense nodes is actually somewhat better. But because there is some noise in the performance of the neural network on the validation set, as we have previously discussed, the best found parameters might actually not be down here. It might be somewhere else. But let's look at the number of dense layers instead. And here we have between 1 and 5 dense layers. And here it found that, it doesn't look like it even matters. The partial dependence plot is flat, which indicates that, yes, the performance might change with the number of dense layers, but there's then another choice of the number of nodes in the layers and the learning rate that compensates for that. So whatever the number of dense layers you choose for this simple MNIST dataset, we can just find another choice of parameters for the other dimensions that will give a good performance instead. And we also have these partial dependence plots when we vary two hyperparameters simultaneously. So here we see that this yellow region here appears to be good. So we have a learning rate in this range here and a number of dense nodes that seems to be the whole range that performs quite decent. Now what you should keep in mind is that this contour plot or this landscape plot is just an estimate. It is estimated from only 40 samples of the actual fitness function. So if you run this again, you might get a contour plot that looks somewhat different. You could also try running, say, 100 or 200 evaluations of the fitness function and see what you get instead. And because the Bayesian optimization is so effective at quickly finding good regions of the search space, this might be more accurate near the optimal points. And if you go out in these areas where it hasn't sampled very much, the estimate might actually not be very good for the true fitness landscape. And if we look at the contour plots down here, what we see again is that the learning rate has a big effect on the fitness, while the number of dense layers doesn't seem to have. And similarly, the number of dense nodes, it seems that higher number of dense nodes is better, but for some reason, the best point that we found was actually located here. But again, this might be due to slight noise. We can also show another type of plot, which is done with this function here. And on the diagonal, we now have histograms which show how many samples were taken during the hyperparameter optimization for each of these search-based dimensions. So we have the learning rate here, and it appears that it has sampled more learning rates in this region here. And again, if we scroll down a little, we see that these are learning rates between 10 to the power of -2 and 10 to the power of -4. And we have the same for the number of dense nodes, and it seems that it has sampled fairly broadly in the entire range, but more in the boundaries of the range. And then we have the number of dense layers, and it seems that it has sampled fairly evenly over the entire range. And these plots here show like the time progression of the samples. So the best parameters that we have found are marked by this red star. And these dots are all of the hyperparameters that we have tried. And there should be 40 of these. And the dark ones are the first ones. And the bright yellow ones are the last ones. And if you had used, say, 200 samples in the hyperparameter optimization instead, then you would probably see that these would start to become concentrated in the best region of the search space. But because we have only taken 40 samples of the search space, they actually spread out quite a lot. And then we can go into TensorBoard, and this shows the training progress of each of those 40 neural networks that we have tried. So first we go up here, tooltip sorting method, and we take descending, so that now when we hover over one of these, we get a list of all of the neural networks that we have trained, and we can see the one on the top has a learning rate of 4 times 10 to the power of -3, approximately, and it has 3 layers, each of which has 311 nodes, and it uses the ReLU activation function. And if we go over here and take smoothing off, what we see here is the classification accuracy that is recorded during training of the neural network, and the loss value, and the classification accuracy on the validation set, and the loss value on the validation set. And we only used 3 epochs during the training of each of these neural networks. But what you should imagine is that you might have 100 epochs, in which case you would be able to better see here what are the tendencies during training of the neural network, and which hyperparameters tend to have a good performance earlier during the training, and which ones have a tendency to stagnate, and so on. Another cool thing is that we can click on graphs so that we can see the architecture for each of these neural networks. And we can select which neural network we want over here. Let's say this one, for example. Then it loads it and shows it. So in this case, they are fairly simple because we are really only changing the number of dense layers. But imagine that you had hyperparameters for a more sophisticated architecture. Then you could get a nice overview of how the resulting neural network looks. Okay, so let's go back to our notebook, and we can then use Keras to load the best model that we have found with the best choice of hyperparameters. And remember that we have saved this during the training. And then we can run this model on the test set, and what we get out is a classification accuracy of 98.88%. We can also use that to predict on new data. So the way you would do this is you would load some new data from disk or wherever. And here we just take a few images from the test set, and then we call model.predict on these images. And then we get the predicted classes. And then we can use our helper function to plot the images and the true and predicted classes. And in this case, they all correspond. So these are all correct. We can also plot examples of images that have been misclassified. So we call model.predict on the entire test set, and we get the predicted classes. And this one was predicted as an 8, where it should have been a 9. And this was predicted as a 3, and it should have been a 5. And I think this is okay, because this is really hard to see for a human as well. And this one is supposed to be a 2, but it was predicted as a 7. I actually think that this looks more like a 7. And this is supposed to be a 5, but it was predicted as a 3. And again, I think this is on the edge. This is okay that it has been misclassified, and so on. So the conclusion is that we have used scikit-optimize to find the best hyperparameters for a neural network. And this is an awesome and extremely powerful tool. I do have mixed feelings about it. I don't think the implementation is very good. And one of the problems is that the code is not documented very well. And there's only a few people who are working on it. And when they stop working on it, there's a big risk that nobody else will understand what they have done. And then it will become abandonware that nobody can modify. I have made an entire separate video on how I think this could be improved. So if you have some spare time and you want to participate in what could be a really important library in machine learning, you might want to spend some time on this scikit-optimize. And as usual, you can download this notebook by clicking on the link below the video.